Hello everyone. In this video, we're going to start looking at the second big piece of calculus, which is integration or antiderivation. So essentially going the opposite from what we're doing when we take derivatives. So for that, we start with the idea of a differential equation. So those are equations that have derivatives in them. They can have multiple derivatives, they can have first derivatives, second derivatives, etc. We're going to look at just simple first order differential equations. In other words, they only have first derivatives. We can solve them using antiderivatives. An antiderivative being, as I mentioned, the inverse operation of a derivative. So let's look at this first fairly straightforward differential equation where we have dy dx equals 2x. Essentially, the solution to this equation is going to be what function or functions have this derivative. So find y, basically. And for that, I'm going to start by actually separating out the differentials in this derivative. So what that means is I'm going to multiply both sides of this equation by dx. So I get dy equals 2x dx. And I'm going to actually even write a 1 here. So basically I have 1 times dy equals 2x times dx. What this means then is I can antiderive both sides of this equation with respect to the variable on that side of the equation. So I've separated out, so I have everything with a y in it on the left side and everything with an x in it on the left side, or sorry, on the right side. And I can antiderive. Now the notation I'm going to use for antiderive, so the thing that says take the opposite of the derivative of both sides of this equation, is this sort of elongated, stretched out s. There's a bunch of reasons why this is the notation, and we'll explore them a little bit as we get into the different uses of antiderivatives, also called integrals. But to start off with, at its most fundamental, at its most basic, it means what function has this derivative. So in other words, on the left-hand side, I'm asking what function of y, so in other words, what expression that has y as its variable has a derivative of 1. And the fairly straightforward answer, the simplest answer is, well, y. The derivative of y would be 1 if y were my independent variable. So the antiderivative of 1 is y. I have to be really careful here, though, because there is also the potential that I have some constant here. Because, yes, the derivative of y is 1, but also the derivative of y plus 7 is 1, or the derivative of y minus 900 is 1. So I'm going to say, well, there's some constant. I'm going to call it C1 because I'm actually going to get a constant on the other side as well. There's some unknown constant. And given the context of this problem, it's an unknowable constant. Essentially, I know that the antiderivative of 1 is some line that has a slope of 1, but I don't actually know where that line is. So in this case, the constant would represent the y-intercept of that function, and it could be any number of functions anywhere up or down this line. They're all vertical translations of each other. They all have slopes of 1, but they have different constant values. Likewise, on the right-hand side of the equation, I'm saying, okay, if now my independent variable is x, what function will have a derivative of 2x? So a function that will have a derivative of 2x is x squared. The derivative of x squared is 2x, but again, plus some constant, because I don't know actually if there has been a vertical translation. So essentially, these antiderivatives don't define single functions, they define families of functions. So I could have just y equals x squared. That has a derivative of 2x. But I also could have it translated down or translated up. And all of those would have the same derivative. Because the derivative of a constant is just 0, there's no way to know if it was there or not. Now, in practice, we don't actually bother with two separate constants. In practice, what we would do is just write this as y equals x squared plus c. Because these are both just arbitrary constants, I could always just combine them. And y equals x squared plus c is then what's called the most general antiderivative of 2x. So any function that has x squared plus some constant is going to have a derivative of 2x. If I wanted you to be able to find the value of c, I would have to give you what's called an initial condition. So something like find dy dx equals 2x. Oops, I don't really need the brackets there. I guess they don't hurt anything. If y at, let's say, 1 equals 10. So if that were the case, if I now know that for that function, when x equals 1, y equals 10, knowing that the antiderivative is y equals x squared plus 2 plus some c, I can say, well, if y equals 10 would be 1 squared plus some constant. The constant, therefore, has to be 9. So in this case, the specific antiderivative would be y equals x squared plus 9. So I can find the constant if I have at least one point on the function. Otherwise, you just have to leave it as a constant, an unknown constant. So let's look at, actually, I'm going to give you sort of a general rule here. Basically, the reverse of the power rule. So we know that when we are deriving x to the power of n with respect to x, we get n times x to the power of n minus 1. So when we're going the opposite way, the antiderivative of x to the power of n with respect to x is actually going to be x to the power of n plus 1 divided by n. So that is what we end up with for antiderivatives. It's basically the opposite of the power rule. These things are connected to each other. Plus, of course, a constant, because we do not know if there has been a translation or not. I will also note that this does not apply it's not divided by n, it's divided by n plus 1. So this does not apply if n equals -1. And we'll actually come to the antiderivatives of that a little bit later. Although if you think about what we learned in our transcendentals unit, you may be able to figure out. But essentially what that's saying is that the antiderivative of x to the power of -1 dx does not follow this rule. And actually just that is the natural log of x plus c, because the derivative of ln of x was 1 over x. The reason that the power rule doesn't work there is because then I would have x to the power of 0 divided by 0, which is clearly not possible. All right, so that power rule allows me to antiderive any polynomials. So looking at this polynomial here, just looking at the individual parts, and again, here we just have our notation. Essentially, it's understood that this means y equals that. The antiderivative of 3x squared is x cubed. The antiderivative of minus 6x is going to be minus 3x squared. The antiderivative of 7 is going to be plus 7x, and then plus some constant. So if I'm thinking about how that fits with the formula, it's 3x to the power of 3 over 3, minus 6x to the power of 2 over 2, plus 7. Now, this is 7x to the power of 0, essentially, so that becomes x to the power of 1 over 1, and then plus some constant. So this polynomial right here, this cubic polynomial, is the antiderivative of the quadratic given. Now, if I have things like these transcendental functions, I have to think about what I know about the derivatives of these functions. Now, the nice thing for e to the power of x is because the derivative of e to the power of x with respect to x just is e to the power of x, that means that the antiderivative of e to the power of x with respect to x is also e to the power of x, although plus now a constant. However, in this case, I don't have e to the power of x, I have e to the power of 8x. So the chain rule would come into effect if I were to just say, I can't just say the antiderivative here is e to the power of 8x, because if I were to derive e to the power of 8x, so thinking about what I would get if I derived e to the power of 8x with respect to x, I would get e to the power of 8x, but then I would have to multiply it by 8. But I don't have an 8 here, so clearly at some point I've divided by 8. So in other words, the antiderivative here is e to the power of 8x over 8, and then always, always, always plus a constant. And we could verify if I derived the e to the power of 8x, I would get the e to the power of 8x times 8. I would divide by 8, which would leave me just with e to the power of 8x, which is what I have. Now, that was a relatively simple, adjustment to make for the coefficient, but sometimes they're not that straightforward. So what we can do is a substitution here. what I can do is I can say let u equal 8x, in which case du equals 8 dx. Or that tells me I can replace dx with 1/8 du. So now the antiderivative of e to the power of 8x dx, or the integral of e to the power of 8x dx, is equivalent when I do these substitutions to e to the u times 1/8 du, which the 1/8 is just the coefficient. The antiderivative of e to the power of u is just eu, e to the power of u, and then plus some constant, where I then replace u with the 8x. So that's a substitution you can do to help you figure out the coefficient adjustment if you need to. It's not work I need to see. Something like the antiderivative or the integral of 3 sine x dx. Now the coefficient here, because it's not part of the argument, I can write this coefficient inside or outside. These are equivalent. So again, thinking of what function gives me a derivative of sine x. So sine x shows up when I derive cosine of x. So in other words, the derivative of cosine of x with respect to x is the sine of x, which means that there is, it's negative sine x, which means that there is a cosine in the antiderivative of sine, but it actually has to be negative so that I would end up with a positive sine x. So what this tells me is that the antiderivative of sine x dx has to be negative cos x plus some constant. So in this case, where I have 3 sine x, what I'm going to end up with is negative 3 cos x plus c. When in doubt, you can just derive that again and see, would I end up with 3 sine x? And I would, because negative 3 cos x would become negative 3 times negative sine x, which is going to become positive 3 sine x. And the derivative of that constant is just going to be 0. All right, what about a radical function? So here's another case. Radicals follow the power rule, so I can use the power rule. But here's another case where substitution can be helpful. Because if I had something to the power of 1/2, so x to the power of 1/2 dx, the antiderivative of that would be x to the power of 3/2 divided by 3/2, or in other words, 2x to the power of 3 over 2 over 3, plus, of course, and always some constant. But I have something more complicated than just x. So when I see that, I'm going to do a substitution. U equals 5x minus 9, because then I'll just have u to the power of 1/2. But that does also require changing the differential part, changing the dx. So this means du equals 5 dx, or what's more helpful here is that dx is 1/5 of du. So this integral is now equivalent to the antiderivative of 1/5. Now I'm going to put the 1/5 out front because it doesn't matter where I put the coefficient. So 1/5 u to the power of 1/2 du, which is 1/5 times, we've just decided that the antiderivative to the power of 1/2 is going to be 2u to the power of 3 over 2 over 3, and then plus a constant, which is 2. Now remember, u isn't actually u, it's 5x minus 9 to the power of 3 over 2 all over 15 plus some constant. So there is my antiderivative. So simple u substitutions can be very helpful when we're trying to figure out what's going on with coefficients. Again, you wouldn't necessarily have had to do that here because you might just be able to recognize, oh, well, the derivative of 5x is 5x minus 9 is 5, so I need a 1/5 factor to account for the chain rule. Essentially, these substitutions allow us to undo the chain rule of derivatives. There's practice in your Read textbook, section 14.1, and Stewart is in sections 9.1 and 9.2 for these antiderivatives. Just one quick comment on vocabulary. The antiderivative, or antidérivé in French, but also these are what are called the indefinite integral. The integrals can be definite or indefinite, and we will get to some definite ones in a little bit. Definite ones have numerical answers, whereas indefinite ones are where we're going to get a function. For any one of these functions, these are very general because I just have plus c. I don't know what c is. But for any one of these functions, if I gave you a point on the function, then you would be able to